Okay, now on sounding the tuning for A with another tuning for B with the frequency 384, 6 beats per second are produced. After loading the prong of A with the same wax and then sounding it again with B, 4 beats are produced per second. What is the frequency of the tuning for A? 388 Hz, 378 Hz, 380 Hz or 390 Hz. So basically here we have the frequency of A tuning fork and the frequency of the B tuning fork, which is given to be 384 Hz. Okay, the beats produced X will be here the beats produced are 6 beats per second. Okay, so hence here after the beat production the frequency is decreasing, so hence we have the frequency of A minus the frequency of B, which equals to the beats produced X. So we can correct this equation as NA is equals to X plus NB. Okay, so NA gives you X, that is 6, plus NB is 384. So the answer of NA comes out to be 390 Hz. So the correct option is D, 390 Hz. Next question, when the temperature increases, the frequency of a tuning fork. When the temperature rises, the frequency of the tuning fork decreases. That is because of the elastic properties are modified when the temperature is changed. Okay, so basically there is a decrease in the frequency of the tuning fork. The correct option is B. Okay, next thing, a tuning fork of known frequency 256 Hz makes 5 beats per second with the vibrating string of a piano. The beat frequency decreases to 2 beats per second. When the tension in the piano string is slightly increased, the frequency of the piano string before increasing the tension is 256 Hz. It is 256 to 2 Hz, 256 plus 2 Hz or 56 minus 5 Hz. Okay, so we'll first write down we are having the frequency N, that is of the piano, so we write it NP, that is the frequency of the piano, which we need to find out, we don't know. Then we have NF, that is the frequency of the tuning fork, that is given as 256 Hz. Okay, so then we have given the beats per second, so X, which is equals to 5 beats per second. Okay, so beats per second are decreasing, and the tension in the piano, the tension in the piano string is slightly increasing. So you have an increase in NP and we have a decrease in the X. So your equation for the NF equation can be written as NF minus of NP gives you X. Okay, so therefore NP is equals to NF minus X. Okay, so that becomes 256 minus 5. So your correct option is option B, 256 minus 5. Okay, next question, the distance between the nearest node and antinode in a stationary wave is lambda, lambda by 2, lambda by 4 or 2 lambda. So basically in the wave we have the antinode, we have the node, again we have the node, we have antinode, we have antinode, we have nodes. So the distance between the two closest nodes and antinodes is lambda by 4. So we have the correct option C, lambda by 4. Okay, the phase difference between two particles situated on both the sides of a node is, basically the phase difference on the of any two particles which situated on the both different sides of the nodes have the phase difference of 180 degrees. So C is the correct option, 180 degrees. The equation of a stationary wave along a stretched string is given by y equals to 5 sin pi x upon 3 cos 40 pi t, where x and y are in centimeters and t is in seconds. The separation between the two adjacent nodes is 1.5, 3 centimeters, 6 or 4. So basically we had the equation y is equals to 5 sin pi x upon 3 cos 40 pi t. Okay, we'll compare this equation with our standard equation. Y is equals to 2a sin 2 pi x upon lambda into cos 2 pi vt upon lambda. So we get that this 2 pi upon lambda is equals to pi upon 3, where the value for lambda is 6. Okay, and the distance between the separation between two adjacent nodes comes out to be lambda by 2. So we have 6 upon 2, that is 3 centimeters is the distance. So your option B is the correct option. At nodes in the stationary wave, change in the pressure and density is maximum, change in the pressure and the density is minimum, strain is 0 or the energy is minimum. Basically when the particle in a stationary wave at the nodes, the energy is minimum, also the pressure and the density is maximum over there. So hence we have two correct options over here, A and D. A wave represented by the given equation y is equals to a cos kx minus omega t is superimposed with another wave to form a stationary wave such that the point x equals to 0 is a node. The equation for the other wave is, Okay, so we have a wave which is given by the equation y equals to a cos kx minus omega t. Okay, so since the point at point x equals to 0 is suppose if the point x equals to 0 is a node, this means that the reflection is taking from the x equals to 0 point. So that means the reflected ray the ray which is reflecting, it takes place from the fixed end, and hence the reflected ray, it must suffer at phase angle of pi. Okay, so if the equation for the incident ray is y is equals to a cos kx minus omega t, then for the incident ray the equation should be y is equals to a cos kx minus omega t plus pi. That means the equation y is equals to minus a cos minus kx. The equation will be minus kx. So omega t plus kx minus a cos omega t plus kx. So that is the equation for the other wave which is coming. So y is equals to minus a kx plus omega t. So option B is the correct option for the another wave. Now the equation y is equals to 0.15 sin 5x cos 300t decreases. Cos 300t describes a stationary wave. So the wavelength of the stationary wave is 1.256 centimeters, 2.512 meters, or 0.628 meters. Basically we need to find the wavelength. So we compare the equation. We have the equation y is equal to 0.15 sin 5x cos 300t. Comparing this equation with the general equation which we have 2a sin 2 pi x upon lambda into cos 2 pi vt upon lambda. So we have 2 pi upon lambda is equals to 5. So lambda becomes equals to 6.28 upon 5. That is 6.28 upon 5. So lambda value of lambda is 1.256 meters. Okay, so B is the correct option, 1.256. The standing wave has 3 nodes and 2 antinodes. Is formed between the two atoms having the distance of 1.21 angstrom. Between them, the wavelength of the standing wave is 1.21 angstroms, 2.4142 angstroms, 6.05 or 3.63. So we have a standing wave which is having a node, 3 nodes, 1, 2 and 3, and 2 antinodes between them. Okay, so that is this kind of a wave which will be forming. Okay, so the distance between the two particles is 1.21 angstroms, so its wavelength will also be 1.21 angstroms. A. So A is the correct option. A string vibrates according to the equation y equals to 5 sin 2 pi x upon 3 cos 2 pi 20 pi t, where x and y are in centimeters and t in seconds. The distance between the two adjacent nodes is, again we have, so we'll write the solution. Y is equals to 5 sin 2 pi x upon 3 cos 20 pi t. We'll compare this with our general equation y, which is equals to 2a sin 2 pi upon lambda, 2 pi x upon lambda into cos 2 pi vt upon lambda. So we get this 2 pi upon lambda is equals to 2 pi upon that will be equals to 2 pi upon 3. So therefore your lambda, the value for your lambda becomes equals to 3. That is the distance between the two adjacent nodes. That is your wavelength. So the distance between the two adjacent nodes is given by lambda upon 2. That is we have 3 upon 2. That it gives you value 1.5. So your correct option is D, 1.5. Waves are approaching each other with a velocity 16 meters per second and frequency n. The distance between the consecutive nodes is 16 by n, 8 by n by 16, or 8 by n, or n by 8. Okay. So we have the distance between the two consecutive nodes, which is equals to lambda by 2. That is the distance between two consecutive nodes. It is given by, it is lambda. We can write it up lambda in the terms of v, velocity and frequency. We had v upon n, that is v upon 2n. It becomes, the distance is given to be each other with the velocity of 16 meters per second. So 16 upon 2n, so it becomes 8 upon n. So your value is B, which is equals to 8 upon n. Standing waves are produced in a 10 centimeter long stretch strings. If the string vibrates in 5 segments and the wave velocity is 20 meters per second, the frequency is 2 hertz, 5 hertz, 4 hertz or 10 hertz. So basically here we have the string which is vibrating in 5 segments. So we have 5 into lambda by 2, which is equals to its length. So therefore the value for lambda becomes twice of L upon 5. Okay, hence now we have the frequency which is equals to velocity upon the wavelength. Okay, so again we'll substitute the wavelength over here. We get it to be 5 multiplied by the velocity upon twice of L. Now the 5 multiplied the velocity is given to be 20 upon 2 into the length is 10. So that gives you 5 hertz. Okay, the frequency comes out to be C, that is 5 hertz. A stretch string of 1 meter length and mass 5 into 10 raised to minus 4 is having tension of 20 Newton. If it is plucked at a 25 centimeter from one end, then it will vibrate with the frequency 100 hertz, 256 hertz, 200 hertz or 400 hertz. Okay, so here we have we know that the plucking distance from one end is plucking distance from one end is 1 upon 2p. Okay, it is L upon 2p, sorry, it is L upon 2p. So we have 25 centimeters the distance from one end, which is L upon 2p, where 25 is equals to L the distance is 1 meter. So we get 100 upon 2p. So the value for p comes out to be 2. Hence now the frequency of the vibration is n, which the formula goes as p upon 2l under root t upon m. Okay, so next p is given by 2 upon 2 into 1 upon under root. The tension given is 20 upon the mass is 5 into 10 raised to minus 4. So calculating the entire thing, the value comes out to be 200 hertz. So the frequency is given is 200 hertz, it is B. If a vibration of a string is to be increased by a factor of 2, then the tension in the string must be made half, twice, 4 times or 8 times. We know that the vibration in the string is directly proportional to the under root of tension. So we have tension is equals to n square. Okay, so here we are making the tension vibration to be increased by a factor of 2. So 2 square, that gives you T is equals to 4 n square. So that means the tension in the string must be made 4 times. A stretched string of length L fixed at both the ends can sustain the stationary waves of wavelength lambda, given by lambda equals to n square upon 2l, lambda equals to l square upon 2n, lambda equals to 2l upon n, lambda equals to 2ln. Okay, for the wavelength we have the formula lambda is equals to 2l upon p, where p becomes the number of loops. You can use n. So here we have the correct option, lambda, which is equals to 2l upon n. String of a musical instrument is 50 centimeters long and its fundamental frequency is 270 hertz. If the desired frequency at 1000 hertz is to be produced, the required length of the string is 13.5 centimeters, 2.7 centimeters, 5.4 centimeters or 10.3 centimeters. Okay, so we have that the frequency is directly proportional to 1 upon L. Okay, so the ratios of the frequency to the L for the two strings, we have two strings. Okay, the required length for the two strings will be L2 upon L1, which is equals to N2 upon N1. Okay, so we can have the equation for N2, that is equals to L1 N1 upon N2. Okay, so L1, the value for L1 given is a string, it is 50 centimeters multiplied by N1 given is 270 upon the frequency of the desired frequency is 1000. Okay, so after solving this, the value comes out to be 13.5 centimeters. That is the L2, that is the desired length. The required length of the string should be 13.2 centimeters. So the 13.5 centimeters. So the correct option is A. Transverse waves of same frequencies are generated in two steel wires A and B. The diameter of A is twice to that of B and the tension in A is half to that of B. The ratio of the velocity of waves in A and B is 1:3 root 2, 1:2, 1:2 root 2 or root 2 is to 1. Okay, so here we are having the equation for the velocity, which is equals to under root tension upon the mass T by m. So we can convert it T upon pi r square rho. Okay, we have the equation for the mass. So we can have the t upon pi r square rho. Okay, then we have we from the equation we know that v is directly proportional to under root t upon the r square. So we can bring the r outside, so r, so that becomes you under root direct under root t upon r. So the velocities of a and b of the steel wires va upon vb, the ratios of the velocities of a and the b wire in terms of the tension and the tension and the diameters, that is the radius, we have under root ta upon tb, they are directly proportional to both of them, into rb upon ra, inversely proportional to the radiuses. So we have ta upon tb is half, the diameter of a is twice to that of b, and the tension is half to that of b. So ta upon tb is half, so root of half multiplied by rb upon ra is twice, and it reverses, so it also becomes half. So the value becomes 1 upon root 2 into 2, so that becomes 1 upon 2 root 2. So the ratio for va upon vb is equals to 1 is to 2 root 2. So cb is the correct option. Sonometer wire resonates with the given tuning for forming standing waves with the given with the given antinodes between the two bridges when a mass of 9 kg is suspended from the wire. When this mass is replaced by a mass m, the wire resonates with the same tuning force, forming 3 antinodes for the same position of the bridges. The value of this mass is 25 kg, 5 kg, 12.5 kg, or 1.25 or 1 upon 25 kg. Okay, so basically we have the equation for the frequency n, which is equals to p upon 2l under root t upon m. Okay, so we have a tuning fork with 5 antinodes. So with the number of here the antinodes is 5 antinodes with the mass of 9, so the tension will be 9 grams. Okay, with the mass of 9 kgs. Okay, sorry, with the mass of 9 kgs, so tension will be 9 and the p will be 5, that is the number of antinodes. So your n1 becomes 5 upon 12 under root 9g upon n. Okay, when with the 3 antinodes we have p equals to 3, the mass is replaced by a mass m, the wire resonates with the same tuning for forming 3 antinodes for the same position of the bridge. The value of m is, we have 3 antinodes and the hanging mass m we need to find. Okay, the hanging mass we are giving it to be capital M. So with p equals to 3 and t equals to, so for instance will take t equals to m into capital small g. So your n2 becomes equals to 3 upon 12 under root capital M g upon small m. Okay, so comparing the n1 equals to n2, we get that 5 upon 12 under root 9g upon m is equals to 3 upon 12 under root capital Mg upon small m. Okay, so the value of, on solving this equation, the value of the capital M comes out to be 25 kgs. So option A is the 25 kgs is the correct option. Two uniform strings A and B made of steel are made to vibrate under the same tension if the first overturn of A is equal to the second overturn of B, and if the radius of the A is twice that of B, then the ratio of the length of the string is 1:2, 1:4, 1:3 or 1:6. Okay, so we are given as the first overturn of A equals to the second overturn of B. Okay, so that means that the second harmonics of A equals to the third harmonics of B. That is the second harmonics of A equals to the third harmonics of B. Okay, so we have the frequencies N2, second harmonics equals to the third harmonics of B. So we can write it in another pattern. So we have second harmonics of N1 of A is equal to the third harmonics of N1 of B. Okay, so we have the formula N1 is equals to 1 upon 2L under root T upon pi r square rho. Okay, so 1 upon 2L under root T upon pi r square rho. So applying both the formulas over there, we can remove this r square outside. We can under root we can remove this r square outside. So okay, so two uniform strings A and B made of steel are made to vibrate under the same tension if the first overtone of A is equal to the second overtone of B, and if the radius of A is twice that of B, then the ratio of the length of the string is 1:2, 1:4, 1:3, 1:6. Solution. So the first overtone of A equals to the second overtone of B. That means the second harmonics of A equals to the third harmonics of B. That means N2 equals to N3. So in terms of the first overtone N1 or N1, we have the second overtone of A becomes equals to the third overtone of B. So we have the formula N1 is equals to 1/2L under root T upon pi r square rho, where r square it is a squaring, so we can move one r outside. So then your equation becomes 2 into 1/2 L of A r of A under root T of pi rho, okay, which is equals to 3 into the bracket L 2 of L of B r of B into T of pi rho. That entire thing will come under root. Okay, so after doing that, after comparing we get LA upon LB, the length which is of YA and B is equals to 2/3 of the distance RB upon RA. So therefore LA upon LB will be equals to 2/3 multiplied by RB upon, we have given the condition that the radius of A is twice to that of B. So A will be twice to that of B. So RB A is given to be twice to that of B. So RB upon RB, okay, RA is equals to twice to that of RB. So we have LA upon LB is equals to, after solving this RB gets cancelled, 2 gets cancelled, we get the ratio to be 1:3. So your correct option is B, 1:3. The sound carried by the air from a sitar to a listener is a wave of the following type: longitudinal stationary, transverse progressive, transverse stationary, or longitudinal progressive. So whenever the sound is produced in the guitar, the observer receives the sound which is a longitudinal wave and this is a progressive wave. So the answer is option D, it is a longitudinally progressive wave. Two vibrating strings of the same material but length L and 2L have radius 2r and r respectively. They are stretched under the same tension. Both the strings will vibrate in the same fundamental in their fundamental modes. The one of the length L with the frequency n and the other with the frequency n2. The ratio of n1 to n2 is given by 2, 4, 8 or 1. Okay, so we have the fundamental frequency n which is equals to 1/2L under root T upon pi r square rho. Okay, so where here we are having the n to be the mass of the unit length of the wire. So here n is directly proportional to L, here n is directly proportional to 1/LR. Okay, n is directly proportional to 1/LR. So we have the ratio of n1 upon n2. We need to find the ratio of the frequency of first to the other. In terms of the radius, it is r2 upon r1 multiplied by the length L2 upon L1. So here r upon the radius of the first is r and 2r, they having the radius r and 2r respectively for the two strings. So we have r and 2r, r upon 2r multiplied by the lengths L and 2L, that is 2L upon L. So comparing both of them, we get 1:1 is the ratio for n1 upon n2. So correct option is D, 1:1. For the stationary wave y is equals to 4 sin pi x upon 15 cos 96 pi t. The distance between the node and the next antinode is 7.5, 22.5, 15 or 30. Okay. So we have the equation y equals to 2 sin 2 pi x upon lambda cos 2 pi vt upon lambda. That is the general equation, and we have the equation given in the question: 4 sin pi x upon 15 cos 96 t. So we compare the equation. So we get, after comparing, we get 2 pi upon lambda is equals to pi upon 50. So the wavelength lambda becomes equals to 30. Okay, now we have lost the distance between the nodes and the next antinode. So distance between the node and the next antinode is given by lambda by 4. So lambda is 30 upon 4, that gives you 7.5. So the distance is 7.5. So option A is the correct option. Two sound waves of slightly different frequencies propagating in the same direction produce beats due to interference, diffraction, polarization, or refraction. So that sound waves which are of different frequencies propagate in the same direction, they produce the beats due to the interference. Okay. When a guitar string is sounded with a 440 Hz tuning for a beat frequency of 5 Hz is heard. If the experiment is repeated with a tuning fork of 437 Hz, the beat frequency is 8 Hz. The string frequency is okay. Suppose if we have the frequency of the string which is equals to 440, which can be increased or decreased by plus minus 5. So of beat frequency of 5 Hz is heard, so it can increase or decrease by 5. If the frequency of the tuning fork it decreases, then the beat frequency also increases. Okay, so and therefore the frequency of the tuning fork will increase by 450 plus 5, that gives you 445. Okay, so the correct option is 445. Two tuning forks A and B give 4 bits per second when sounded together. The frequency of A is 320 Hz. When some wax is added to B and it is sounded with A 4 bits per second, again heard, the frequency of B is 312 Hz, 316 Hz, 324 Hz, or 328 Hz. 8 Hz. So we have two tuning forks here. So the frequency of NA and NA gives 4 beats per second. So and we have two frequencies NA and NB. When sounded together, the frequency of A is 320 Hz. So NA we are having is 320 Hz. When some wax is added to B, we have to find the frequency of the B. Okay, so after the tuning forks are strike at the rate of 4 beats per second, now the frequency goes on decreasing. So we can have NA minus NB is equals to the X, that is the beats per second. But in that case we have the B which is decreasing, so we can have NB minus NA which is equals to X. So this is the correct equation for this. So again we have NB equals to X plus NA, and the beats per second is 324 beats per second plus the frequency is 320, so that gives you 324 frequency of the NB after. So C is the correct option. When two sound waves are superimposed, beats are produced when they have different amplitudes and phase, different velocity, different phases, or different frequencies. When the two sound waves are produced and are superimposed, the beats are produced when they have a small variation in their frequencies. So they should have different frequencies. Beats are produced by two waves given by y1 equals to a sine 2000 pi t and y2 equals to a sine 2008 pi t. The number of the beats in each per second produced in each per second are 0, 4, 1 and 8. So we have the solution. So number of beats produced is equals to n1 minus n2. Okay, so we from the equation 1 we have y1 is equals to a sine 2000 pi t and y2 equals to a sine 2008 pi t. So we have omega 1 is equals to 2000 pi and omega 2 equals to 2008 pi. Okay, so omega is equals to 2 pi n1, so therefore n1 becomes equals to 1000 t 1000. Okay, so again omega 2 is equals to 2 pi n2, so n2 becomes equals to, here dividing the 2008 by 2, they will give 1004. Okay, so the number of beats produced is n1 minus n2. So we have n1, that is 1104 minus 1000, that is equals to 4 beats per second. So number of beats per second is 4c. The beats are produced by the sound source of same amplitude and are nearly equal frequencies. The maximum intensities of the beat produced will be dashed to that of the one source, same, double, 4 times or 8 times. So basically we have the formula intensity, which is directly proportional with the amplitude square to the square of the amplitude. So In this, for the amplitude max, we have 2 of the amplitude. We I denote this by a naught, where a naught is the amplitude of the one source. So the intensity, the maximum intensity, will be 4 times of the I naught, that is of the intensity of one source. That is the amplitude of the one source. This is the intensity of the one source, IO or AO. So the intensity, maximum intensity, will be 4 times that of the one source. So 4 times is the correct answer. Okay. A sound wave of frequency 170 Hz is placed near a wall. A man walking from the source towards the wall finds that there is a particle rise. There is a particle rise and fall of the sound intensity. If the speed of the sound in air is 340 meters per second, then the distance separating the two adjacent positions of the minimum intensities is 1 by 2, 3 by 2, 1 and 2. Okay, so basically we have given is the frequency, which is equals to 170 hertz, and near the wall a man is walking from the source. The man is walking towards the wall. Okay, so n is given as 270, and we can have the velocity of the sound is 340 meters per second, it is given, and the source towards the wall finds that there is a particle rise and fall of the sound intensity. Okay, so we have v is equals to n lambda, so lambda is equals to v upon n, that gives you 340 upon 170. So the wavelength of the sound is 2. Okay, so lambda becomes equals to 2. So if the speed of the sound in air is 340 meters per second, then the distance separating the two adjacent positions of the minimum intensities is, so for the minimum intensity, the difference of meter separating is half the wavelength. So x may be the difference, that is it can be half the the difference separating between the two minimum intensities is half the wavelength. So that is lambda by 2, that is 2 upon 2, that gives you 1 meters of the distance. So correct option is B, 1 meters. Two tuning forks have the frequency 450 Hz and 454 Hz respectively. On sounding these forks together, the time interval between the two successive maximum intensities will be 1 upon 4 seconds, 1 upon 2 seconds, 1 seconds, or 25 seconds. So the time interval between the two successive maximum intensities is given by 1 upon n1 minus n2, that is 1 upon 454 minus we have 450. Okay, that gives you 1 upon 4 seconds. So A is the correct option. Two tuning forks A and B are sounded together. They produce beats per 4 beats per second. Then it is slightly loaded with wax. They produce 2 beats when sounded again. The frequency of A is 256. The frequency of B will be 250, 252, 260 or 262. So solution, we have n, the frequency of A known beats, which is equals to 256 Hz, and we have to find the frequency of the unknown beats NB. Okay, so after the beats produced is x, which is 4 beats per second. We have the beats production 4 beats per second. So after the beats production, the beats are decreasing, they are decreasing, that is x is going on decreasing. Also the tuning fork is loading, so it is also decreasing, that is the NA is also decreasing. So we can have NA minus of NB, which is equals to this x. So in similar pattern we have NB, which is equals to NA minus x. So NB can be equals to NA is 256 minus of 4, that gives you NB as 252 Hertz. So answer is 252 Hertz. Two tuning forks of frequency n1 and n2 produced n beats per second. If n2 and n are known, n1 may be given by n2 upon n plus n2, n2n, n2 plus minus n, n2 upon n minus n2. So we have the beat frequency is all equals to the number of beats per second. So the beat frequency n it is equals to n2 approximately minus n1 or n2 minus n1. So we have n2 equals to n. So we have n2. In the terms of n1, we can find the answer. We need to find the n1 may be given as. So n1 may be given as n2 plus or minus n. So that is the option number C, n2 plus or minus n. Beats are the results of diffraction, destruction interference, construction and disturbance interference, and superimposition of the two waves of nearly equal frequencies. Basically, beats are the results of superposition of the two waves of nearly equal frequencies. When they interfere, the beats are produced. So D is the correct option. In the experiment to determine the speed of sound using a resonance column, prongs of the tuning forks are kept in vertical plane, prongs of the tuning forks are kept in the horizontal plane. In one of the resonance observed, the length of the resonating air column is close to the wavelength of the sound in air. In one of the two resonance observed, the length of the resonating air column is close to the half the wavelength of the sound in air. Basically, in the experiment to determine the speed of sound, we have the tuning forks which are arranged in the vertical plane, so that we can measure the vibrations of the tuning forks. So the prongs of the forks are kept in a vertical plane. Two waves having the equations x1 equals to a sine omega t plus psi 1, x2 equals to a sine omega t plus psi 2. If the resultant wave if in the resultant wave the frequency and amplitude remains equal to those of the superimposing waves, and the phase difference between them is pi by 6, 2 pi by 3, pi by 4, or pi by 3. So basically, superimposition of the waves, they do not alter the frequencies of the resultant waves and the resultant amplitude. So basically, we have the resultant amplitude, we can add them. So a square will be equals to the a square plus the a square plus 2a square cos of psi. Okay, in the result, that is in terms of the phase difference psi, and so we get 2a square plus 2a square cos of psi. So that becomes 2a square 1 plus cos psi. So as cos of psi becomes equals to minus half, that is equals to cos 2 pi by 3. Okay, so psi becomes equals to 2 pi by 3. So the phase difference between them is option B, 2 pi by 3.